Hey there. Today's lesson we're going to talk about position, velocity, and acceleration and how they relate to one another. There's their abbreviations. They're all functions of time. So position is an S. And if we want to think about a number line with a reference starting point is 0, because that's typically how position is defined, you'll see a preamble of for an object moving along a straight line, its position relative to a fixed point called 0 or some other reference point, okay? At a time where time is greater than or equal to 0, it's going to be given by the position function. So all of these values have the possibility of being positive, negative, or 0. So if this is like a number line, if position is negative, it simply means I'm left of 0. If position is positive, I'm right of 0. If position is at 0, then that's exactly where I'm at. Positive velocity would mean motion to the right. Negative, motion to the left. 0, no motion. Acceleration, think of that as being a push. So a push to the right is positive, a push to the left is negative, no push is 0. I could have had a vertical axis actually. I could have done it this way. And if this is my reference point, this would be positive position, negative position. Positive velocity, negative velocity. Positive acceleration or push, negative push. But for most of your questions, you'll be talking about moving along this line. So we'll go with that as our start. So these things in relation to each other, we really have to watch our wording. Let's say I'm right here. So my position is negative. Okay, when I start to move, let's say my motion is this way. So velocity is positive. Let's say the acceleration or the push is in the same direction as I'm moving, right? So here was me going along my merry way out for a walk and maintaining a certain velocity, but with a push from behind, all of a sudden things start happening. So I was doing this and then all of a sudden this happened. Because these were in the same direction, I could say I speeded up or I sped up, right? Same thing, I could be doing this motion here. I could have been moving to the left. The push could have been to the left. I will still be speeding up. So I don't care if I'm in a negative position or a positive position, I can definitely speed up. But when we're going to use that word speed. Speed and velocity are very different. So in order to speed up, I see I need the direction I'm moving and the push to be in the same direction. But watch the wording. Definitely here, I would say this is a situation where I would speed up. Okay, but if somebody asked me, what happened to the velocity? So let's say originally I'm right here. Okay, so I'm moving to the left. I had a push to the left, so eventually I'm right here. Let's say my original velocity was negative 2 meters per second. Because of that push, maybe by the time I've made it over here, my velocity is now negative 5 meters per second. And now I'm being asked, did my velocity increase or decrease? Well, velocity has direction. Velocity has a quantity, a magnitude to it. So what would you describe this in proper words if you went from negative 2 to negative 5? This is smaller. So my velocity decreased. Okay, so throughout the scenario, the velocity decreased, but I did speed up. So velocity, you have to take into account what the units were. This is smaller than this, so velocity decreased. Okay, so that's something to watch for. Another thing to watch for is when we talk about the wording displacement. Displacement and position aren't the same thing. Position is where are you at. Displacement is the net change. Okay, so quite often that would be delta S, and that's going to be net change in position between two times. Okay, so I could say from time 1 to time 2. So displacement, let's say this is home, so this is 0. Over here is 2 kilometers to the right of home. So I start traveling from home and I make it to here. If I'm done the day, my displacement is positive 2 because that's my net change from where I was at the start to the second time. If I, though, came back home, now someone asked me, what's your displacement? The answer is 0. I am back to where I started. So what was the overall change in my position between those two times? It would be 0. That is not the same as total distance traveled. If someone asks you, what's the total distance? And we have the same scenario here. And I walked here, and I walked here. Well, the total distance is going to be a sum. So I might talk about this as a positive value. I might talk about this as a negative value. But when we're talking totals, it's like you absolute value everything. So now I would say the total distance would be 4. So displacement and total distance traveled are not the same. Okay. I want to go back and talk about this idea of velocity. In our last lesson, we spoke about rates of change, and that's what velocity is. So maybe you want to just kind of listen to there's not too much math going to be going on today. It's mostly definitions and understanding the relationship between these values. So when we talk about velocity, then you could go back and do some notes after. Velocity was a rate of change. That's the key word there. Rate of change of position with respect to time. Okay, so it's change. That's really important. So if I just sat here all day long and didn't move anywhere, why would you ask me what my velocity was, right? There is no velocity. I'm just sitting here. There needs to be a change in position. Time will go by. Time's going to go by no matter what we want. If there's no change in position, there's no velocity. So velocity is going to have units. It's position compared to time. And that word rate, we know what rates look like. We have 2 different units. So it could be something like kilometers per hour, right? That could be a rate. Meters per second. But it will be something showing position compared to time. So when we're showing change, we're talking about derivative. So what is velocity? It's the derivative of position. So position was s at t. So velocity would be derivative of s at t over derivative time. How position is changing as time is changing. Quite often this function notation gets left off. So you could write ds over dt. Or you could really just use prime symbols, so you could write s prime. So this is all the derivative when we're talking about velocity as instantaneous. But we did talk about something else in our first lesson about rates of change. We can have average rates of change and we can have instantaneous. So an average rate of change versus an instantaneous rate of change were 2 different scenarios. Okay, average rate of change was definitely dependent on a time interval. Instantaneous is what it says. It's at a split second in time, so this was derivative. So when you're averaging something, there's some division going on. You have numerators and denominators. So when we were talking about, which one did we do before? Average rate of change here. I forget what we were talking about. Okay, but today we're going to talk about velocity. So if you're asking me for average velocity, that's how something changed as time went on. So there must be 2 time factors, maybe time 2 minus time 1. If I'm looking at between 3 seconds and 10 seconds, this would be 10 minus 3. There's my 2 times. But what must have been changing to end up with velocity? Position must have been changing. And really, let's look back here. Let's say I had to go from here to here, from this spot to this spot. Okay, so yeah, I have a change in position. If you gave me 1 second to get there, that would give me a certain velocity. It would be this distance divided by 1 second. If you gave me 3 seconds, it would be this distance divided by 3 for my velocity. Or an hour, this distance divided by an hour. So the more time you give me, the smaller my velocity would need to be. But it's that comparison. So velocity is comparison of 2 positions. So this is kind of one area where we see a lot of errors. When you see being asked for average velocity, you want to go put velocity here. No, to create velocity, there was a change in position. Now, what would instantaneous velocity be? Derivative. So I'd use my rules, I'd find my formula for derivative. I could say that's S prime, or I could say that's, as we did on the other page, I'm using my derivative notation, or it could be something like this. But these all have units. Maybe this is feet because position would be in feet, and this would be per second. This would have the same units though, position and time. So I could still, because these are rates, end up with the same units, whether I'm talking about average or instantaneous. Okay, what's acceleration? Acceleration means your velocity didn't stay the same. If you just keep going 50 kilometers an hour and that never changes, there was no acceleration. Acceleration came from you changed velocity. So average acceleration came from changes in velocity. So velocity at a certain time minus velocity in another time divided by that time frame. That would be average velocity. And again, you kind of have a tendency to want to put acceleration up here. No, you're comparing how velocities changed. Okay. How about instantaneous acceleration? That's a derivative. What is it the derivative of? It's the derivative of velocity. So I could write it like this. I could say, well, it's the derivative of velocity. I could write it like that. Or I could say dv over dt. And it would have units as well. So velocity could be feet per second, but time was seconds. When you move your units around and make this look the way it really is, you would get this as a unit for acceleration, feet per second squared. The same thing would be here. What's velocity measured in? That would be feet per second. What's time measured in? Seconds. And again, that would resort to the same thing. But there's another way of looking at acceleration. It came from velocity. It came from getting the derivative of velocity. But where did velocity come from? It came from position. So to end up all the way down the ladder to acceleration, you have found the second derivative of position. So another way to talk about acceleration is this is the second derivative of position. So notation would be the second derivative, and notice the location of those exponents. There's the second derivative of position, or maybe we drop that t, and you may have it described like that. And again, it's going to have the same units. This is all about change. Change in position and time changes. Change in velocity as time changes. So that's what derivatives are all about, is talking about change. Okay, I want to go back to that idea and that vocabulary that I was using there about speeding up and slowing down. Okay, because we haven't really done any math yet. So we'll address this idea of what does it mean to speed up. Okay, so speed up. So I can speed up on either side of zero. That doesn't matter. But if I'm heading this way, if my velocity is positive, how could I speed up? If the acceleration is in the same direction, right? So they're both positive. Or if my velocity had been negative, but my push or my acceleration was also negative, both of these scenarios will make me speed up. So look at what's going on. The forces need to be in the same direction. So to come up with a formula, so I can do some math, how will I know when these equations, because they will have equations, will create a speeding up situation? It's when velocity and the product of velocity and acceleration is positive, right? Two positives would create a positive, two negatives would create a positive. So this is just a mathematical way when we say greater than zero of telling people positive. So this could be positive and this could be positive, I'm speeding up. This could be negative, this could be negative, I'm speeding up. So as long as they have the same signs, then I know I'm speeding up. How would you know when you are slowing down? Okay, to be slowing down, doesn't matter where you're at. So I was going this way, I was going negative, but the acceleration was in the opposite direction. I'm going to slow down. Or over here, wherever you're at, if velocity was positive, but the push was in the other direction, okay, I'm slowing down. So do these values have the same signs? No. Now they're going to have opposite signs. So in that scenario, when you have velocities sign times acceleration sign being negative, that's how you know you're slowing down. So opposite signs, positive, negative, or negative, positive. This is notation for negative. Then I know that scenario, I'll be slowing down. And you'll see in an example later today how you could address and answer some questions regarding speeding up and slowing down. But again, remember, I know I'm speeding up, but remember what would happen as this scenario kept going. I'm going left, you're pushing me left. My velocity is becoming more and more negative. Maybe it was -10. Down the road here, it's -20. So velocity decreased because the number was smaller. Okay. To look at a graphical approach, really important here. Okay, if I've got some graphs here, I've got 3 graphs. I've got a position time graph. Then from here I made the velocity time graph, and from here I made the acceleration time graph. Velocity's the derivative, so it shows the slope of position. Acceleration is the derivative of velocity, so acceleration shows the slope of velocity. So if you have a look at this, for a brief time the slope was negative. Then this graph slope was positive. So how do you show that on a slope graph? In a brief region, the slope was negative. So being below here shows negative slope. Being above here shows positive slope. So in that respect, they make sense together. Another idea. Let's say the start of my position would be when time is 0. So I'm starting at -3. So that means on a number line, here's where I'm starting. My day starts at -3. Then look what happens. A half a second goes by. Now I'm at -4. So now I've made it to here. Another half second goes by. Oh, I'm back to -3. So I started here, went to here, now I'm back here. Then time keeps going on and I keep heading to the right. That's the interpretation of this graph. So at a half second, I'm at -4. So that's the farthest left I will ever be on this journey. When we think about the slope right here, the slope is 0. So on a slope graph, that shows up as your x-intercept. I could talk about these values of position and velocity. So this is saying I moved left. I know I moved left. I was at -3. Now I'm at -4. What is this saying? This is all about me moving left. I could talk about okay, I'll get to a different concept later in a minute. If I look at these 2 graphs, what could I get out of these 2 graphs? Now remember that you're reading these as anything for a position graph. Anything above the x-axis means your position was to the right of 0. Anything below, your position was left of 0. If you're here on the x-axis, you're at 0. Velocity graph, above means when you're moving right. Below, when you're moving left. On the x-axis, you're stopped or not moving. Acceleration graph, above, you're being pushed to the right, being pushed to the left, or not being pushed. So these 2 are the ones we've been talking about today in terms of speeding up. When they have the same signs, you're speeding up. So over here, look at your velocity over here. This is negative. You're moving left, okay? So this is the negative value for velocity. This has a constant slope. It's never changing. This guy's slope is some positive value. Let's say it's +2. So how do you show this guy's slope on a slope graph? Forever +2. And the interpretation here is, in this situation, the push is always +2. So the push is always to the right. So you were going left. You were going left. But the push was to the right. You're going to stop and you'll probably reverse direction. And that's what's being said here, right? That's exactly what happened here. You were going left, but the push was right. So it made you stop. And this shows you as well that you stopped. and then you went to the right, and then you were going to the right. These two in conjunction, now I could say, well, this, I'm moving to the right and I'm being pushed to the right. Hey, I'm going to speed up. So I could talk about these two graphs in terms of what that meant in the scheme of things. I'm going to put this in with your notes in case you want to print it out and have a closer look, and again talk about the interrelationship between how these work in conjunction with each other and what does that mean. Okay, so I'm just going to go back here and let's finally do an example. Okay, so typical example, you'll be given an equation representing position. Okay, so my equation is S of t equals t squared minus 4t plus 2. You'll be told this is the describing the position function of an object moving along a line in relation to a fixed point 0. You'll be given units, and of course time starts at 0. Whoop, I'm writing off there, sorry. Time starts at 0, and you'd have to have some kind of units. Oh, that's what happened. Okay, so let's say I'm in centimeters, and let's say time frame is seconds. So how about initial position? What is the initial position of this object? Well, initial position is when time is 0. So position at 0, if you put zeros in there, you get positive 2. So where are you starting this whole journey? You're starting right here. You're starting at 2. Okay, because that was the answer. Where are you after 1 second? After 1 second, I put a 1 in here and I get negative 1. So 1 second later, I'm now here. Okay, so I started here. This took 1 second. 1 second later, I'm right here. Let's do one more. How about if I put in a 2? I'll be at 2. So negative 4, I'll be at minus 2 centimeters. Okay, so give me 1 more second, and now this took 1 more second. So now I'm here. Okay, because those are my positions. If somebody asked me, though, what's the displacement from 1 to 2 seconds? That's asking me, versus where I was at 1 second, where am I now after 1 more second? In other words, where am I at 2 seconds? So displacement is my position at 2 minus my position at 1. We're not averaging, we're just asked for displacement. So my position at time at 2 seconds minus my position at 1 second, because those are the two that I'm being asked here. These could have been any two values. Well, my position at 2 was negative 2. My position at 1 was negative 1. So the displacement is negative 1 centimeters. This doesn't mean I ended up at negative 1 centimeters. That means at 2 seconds versus at 1 second. How are they related? What is my net difference in position? My net difference is that I end up being 1 left of where I was, or where this object was. I'm just saying 1 left of where I was at 1 second. Because this is at 2 seconds. So the negative says I'm 1 left of where I was at 1 second. And look at that works. Here's where I was at 1 second. Here's where I'm at 2 seconds. So where is this compared to this? This is 1 left of where you were at. Okay, you could be asked to find your average velocity. And I'm just going to keep using these 2 times. So what's my average velocity from 1 to 2 seconds? Okay, so how do you find average velocity? You show the difference in position. So position at 2 seconds minus position at 1 second over 2 minus 1. If I go through all that, we just did that up here. We got negative 1 over 1. This would be linear units. This is time. So this tells me at 1 second, I'm heading left. This is a negative value. Well, sure you were. Sure you were. At 1 second, you were heading left. How about you were simply to find the velocity at 1 second? This is now instantaneous, so I need a derivative formula. So a derivative formula comes from differentiating this. So my formula for velocity would be 2t minus 4. So at 1 second, I'll throw a 1 in here. So velocity at 1 is 2 times 1 minus 4, negative 2 centimeters per second. So that's my speed, or I shouldn't say speed, that's my velocity right here, negative 2. So I know I'm going left. Then I'm being asked, hey, how long before I stop? Because we know, or probably I do stop. So how long till it stops? Oops, stops. How do you know something stops? Velocity equals 0. So my formula for velocity was v equals 2t minus 4. So I want velocity to be 0. Now I'll solve for t, and that happened at 2 seconds. So at 2 seconds, I'm now going to stop. Okay. When did, or when does, because we don't know, when did or does the object change directions? Okay, for something to change directions, for sure it has to stop. But don't think that's the only requirement. If you left your house in the morning and every time you stopped, you changed directions, you'd never get to where you were going. So to change directions, for sure our velocity has to be 0. But think about what happened just before that stop and just after that stop. So to change directions, your velocity needed to change signs. So for sure, we got this idea of, we're wondering about at 2 seconds. We know we stopped, but did you actually change directions? I would just use a couple of test numbers. This is probably the easiest way around this. So what would my test numbers be? Just before 2 seconds. So what was my velocity? Maybe at 1.9 seconds. And how about right after 2 seconds? So let's say my velocity at 2.1. So for sure at 2 seconds, I know right smack in the middle of these, I stopped. But what direction was I heading just before and just after? So if I do this one here, I get negative 0.2 centimeters per second. If I do this one, I get positive 0.2. So when did it change directions? At 2 seconds. Had these continued just before, if this were negative, and just after it was still negative, I was just at a stop sign for a minute and then I kept going left. But now I know I did change direction. If you were ever asked for total distance is tough. I mentioned that at the beginning. You're going to have to use absolute value signs and add everything up. Okay, because here was that scenario. We started over here, we're going to come over here, we're going to go over here. We can't just use displacement. I need to take into account every time I stopped, and I'll look at that distance that I went. If that distance happened to be negative, I'm going to just absolute value it and make it positive. So let's say we were asked, in our case here, what's the total distance from 0 seconds to 3 seconds? Well, I've done some preliminary work. I know I stopped at 2 seconds. So I need to break this down. What was the distance that I went from 0 to 2 seconds? I'll make that absolute value. I'll add what distance did I go after the stop, and I will add these two together. So what distance did I go from 2 seconds to, from 0 seconds to 2 seconds? Well, that's my position at 2 minus my position at 0, but I'll absolute value it. What was my position at 3 minus my position at 2, but I'll absolute value it. Because these could be negative values. So when I'm done all this, I think for the first one, I end up with a negative 4 in here. Second one, I end up with a 1. So absolute value is 4, absolute value is 1. I would now know that in 3 seconds, my total distance traveled would be 5 centimeters. Okay. I could be asked, when am I speeding up and when am I slowing down? They could say, it would be nice if they gave me a time and they said, okay, how about at t equals 1? Am I speeding up or am I slowing down? Well, what determined that? My velocity formula and my acceleration formula. So velocity was 2t minus 4. So what's acceleration? 2. So the push is always to the right, forever and ever. So at 1, what was happening? If I put a 1 in here, I will get negative 2 centimeters per second. This is positive 2 centimeters per second. Well, they're in opposite directions. The push and the motion are opposite. So at 1 second, I'm slowing down. And we saw that, right? Here in 1 second, look how far you traveled, or the object traveled. In 1 more second, it went a much smaller distance because it was slowing down. Okay, from a graph, it would be a different perspective, right? I do like I did before, try and find where these graphs were in different regions. If I'm slowing down, it means velocity and acceleration would be a positive and a negative, one of each. Okay, so again, some typical questions. And one more thing I want to talk about here, which is a very common question, is when are you moving toward or away from 0? So think about what that means. If I'm moving towards 0, it could be that scenario or it could be that scenario. What do I know about this scenario? My position is negative. Position is left of 0. My position is negative, but my velocity was positive because I'm heading to the right. Look at this. I'm definitely heading towards 0 here. My position was positive, but my velocity was negative. So how do you know that you are moving toward 0? They have opposite signs. So the product of position and velocity is negative. What would it take to talk about the idea of moving away from 0? To be moving away, this scenario, my position was negative and my velocity was negative. Here, moving away, my position was positive and my velocity was positive. So to be moving away from 0, now they have the same signs. So here their product is positive, here their product is negative. So you could do, again, at 1 second, you could be asked, oh, is this moving towards 0 or away from 0? You could plunk that in. Now, there will come a time when they won't give you the time. They won't say at 1 second. They'll just say, when is the object moving toward 0? Okay. So if you had 2 graphs, that would be very, very easy. You'd look at the position graph, you'd look at the velocity graph, and you'd find areas where one's above the x-axis and one's below the x-axis. But if you didn't have graphs, if you simply had equations, so you have an equation for s at t and you have an equation for v at t, find each of their critical numbers and actually make a sign chart. Make a sign chart for both and you'll have these intervals and you'll be able to see where this one's positive or this one's negative and this one's positive or this one's negative. So we are talking about being able to factor, right? Critical numbers come from factoring, but then you could use the results of these charts to talk about are you moving away from 0 or towards 0. So lots of, there's algebraic interpretations, there's the word interpretations, and there's the graphical interpretations. So I did have, I might put this for you as well. Here are the 3 graphs that we just did. Okay, so the equations that we went through, this one right here is a parabola. And then we did work out the velocity equation. Here they all are actually graphed. So from the graphs, you should also be able to answer questions about moving towards 0. Well, that's when S and V have opposite signs. So I'd look at my S and my V charts. Here's where position is positive and velocity is negative. So in that time frame, I would be moving towards 0. Or what could I come up with from a velocity and acceleration graph? I could come up with speeding up and slowing down answers, okay? So anyway, I'm going to put these on as well if you want to have a look. They'll be there for you to look at. And I might throw in one more. So simply 3 random equations here, or random equations and random graphs. And without doing any algebra, could you answer these questions? When are you moving towards 0, speeding up, and change distance? Lots of information there. Not very much. The math is the breeze. It's the understanding the relationship between all of these quantities. So thanks for listening. We'll we will keep exploring in the next lesson. Bye-bye.